Now we just established that this does converge from the absolute convergence theorem. If the absolute value version converges, we have another term for it. So if summation of the absolute value of an converges, we say the summation without the absolute value version, this one, converges absolutely. So that's an important word, converging absolutely. If summation of an converges, but summation of absolute value of an does not, then we say summation of summation of an converges conditionally. Converges conditionally. Now, why is there a distinction between the two? You might wonder. So, in order to give you some idea of why these two are important concepts, let me give you an example of something that converges conditionally, because this one is an example that converges absolutely, right? The absolute value version converged, so this converges. Okay. So here's an example. Summation of n equals to 1 through infinity of negative 1 to the n plus 1 times 1 over n. Now if you write this explicitly, this is 1 over 1 minus 1 over 2 plus 1 over 3 minus 1 over 4 plus 1/5, something, something, okay? I think last week, or maybe the week before, we showed that this actually converged to log of 2, ln of 2. But we know that this is convergent because of the alternating series test, right? Because the limit of individual things go to 0. 1 over infinity is 0, right? So the sequence limit is 0. And you can also see that the numbers go smaller and smaller. 1/4 is bigger than 1/5, and 1/5 is bigger than 1/6. So as you go further, the numbers shrink down to 0, right? Decays always. And therefore, it meets all the criteria for the alternating series test, these two. So that convergent. On the other hand, if you take the absolute value, what do you get? If you take the absolute value of this, what do you get? What does negative 1 to the nth power do?
That makes it alternate.
Yeah, but if you take the absolute value, what does it do?
It's just positive.
Yeah, it's always positive. So this is the same thing as n from 1 to infinity of?
Just 1 over
Just
n.
1 over n. Does this converge or diverge? It diverges. Okay. So this series is an example of a series that converges, but its absolute value doesn't converge. So it's a series that converges conditionally. Okay. So using this as an example, let me try to explain further why these two concepts are important. Suppose you did something wrong and the king put you into jail, and as a punishment, you're to eat infinite number of apples and infinite number of bananas. Okay? And the guard says, okay, I'll give you the apple, odd days and eat bananas on the even days, right? But let's say you hate bananas and you like apples. Right? So you say, well, I'll just have 4 days of apples and 1 day of bananas. And then the guard will say, no, you can't do that. You're supposed to eat infinite number of apples and infinite number of bananas. And then you counter by saying, hey, it's infinite, right? So it doesn't matter if you eat 4 apples and 1 banana, or if you eat 1 apple and 1 banana. You still get to, if you go to infinity, at the end of infinity, you still have eaten all the apples and bananas. Does that make sense?
Well, because there's no end to apples and bananas.
Yeah. So
Doesn't matter.
or a better way to say this will be something like, if you're given a choice to have infinite number of apples and infinite number of bananas, if it's finite, you really have to alternate, or you have to have equal number of apples and bananas, right? But if it's infinite, then you can have more apples than bananas as you proceed, and still you can go till infinity. It's possible, right? So the great mathematician Friedrich Gauss was the first one to realize that it's like apples and bananas. The positive ones are apples and negative ones are bananas, right? And you're free to choose how many of them to consume each time. And that allowed him to prove a very unintuitive, like very strange kind of paradox, which is that if you have a conditionally convergent series like this, if it converges, then you can actually make it to converge to any number you want by shuffling the order of addition. That's really strange, right? But here's his argument. Let's say, well, I know that this value will converge to something less than 1, but let's say you want to converge to 2. So here's 0, right? How do you make it converge to 2? Well, add 1, right? And then you don't subtract 1/2, you just add 1/3. You add 1/3. You add 1/4, right? You keep adding until we know that the odd ones will add up to infinity. The negative ones, if you add, it will go to negative infinity, right? So because the odd ones will add up to infinity, at some point you will be passing 2. But the moment you pass 2, you have 1 banana. You have one negative. Go back, okay? But you still have lots of apples left, so you keep adding the positive ones, right? Until you pass 2. And then anytime you pass 2, then you add a negative. And you keep doing that until you get closer and closer to 2. So because your step sizes are becoming smaller and smaller as you jump, eventually you'll see that this limit will become 2. Yes?
I think trouble with this. 1/n.
Yeah.
When you add that, it becomes infinity.
Yeah.
But when you add those, don't they also add to infinity eventually?
No. This one converges to see, it's like you're going back and forth with plus and minus, and it shrinks down, right?
Right.
In that case, it has to converge to a single value. Yeah. So this does converge to a value, and we actually did numerical experiments to show that this converges to log of 2. But if you're free to choose the order of that addition, a paradox appears that you can make it to converge to anything. Which means that if you have a series something like this that's alternating, be careful not to change the order of addition. There are some ways to speed up the summation of infinite series by simplifying. Like you might add every 2 sums and try to simplify. There are algorithms like this, but whenever you try to use those algorithms with an alternating series, be careful. That's the moral of the story. Okay.